We have two other videos that look at the measures and methods to determine the efficiency of different algorithms, Big O notation, and a comparison of the complexity of algorithms. You should watch those videos before looking at this one. This is really just a summary of everything that we've learnt so far, and we have a look at Big O notation in practice with games development and collision detection techniques in particular. Most video games require some kind of collision detection. In this example, we've got a very simple spaceship that can fire a missile at an invader. We've got one alien ship and one missile. So a simple way of determining whether the missile has hit the alien or not is just to see if they intersect each other. We can draw an imaginary box around the missile and around the alien and see if the two boxes overlap each other. This is very simple mathematics and is not difficult to program at all. But because we've got one ship and one missile, then the time complexity of the algorithm is never going to change. Let's assume that when the player hits the invader with their missile, the invader disappears and a new invader is spawned. So we're only ever dealing with one missile and one alien ship. If we increase the challenge in our game so that the player has multiple alien ships to fire at, but can still only fire one missile at a time, then we need to check that missile against every single alien ship that's currently in the game. So we can use a simple for loop to achieve this. We can say for each alien in the aliens collection, if the missile has intersected the alien, then carry out the collision handling code. So because we need a for loop in this situation, then we've introduced linear complexity. As the number of alien ships increases, so too does the time complexity of the algorithm. To make the game even more fun to play, we can introduce a multiple missile rapid fire into our game so that the player can fire as many missiles as they like, providing they have sufficient ammunition. Well, now from an algorithmic perspective, we have a real problem because we need to check every missile against every invader. And to do this, we might have a nested loop. We might say for each missile in the missile collection and for each alien in the alien collection, check if that missile has hit that alien, and if so, do the collision handling code. It's the only way we're going to check every missile against every alien ship. But the problem here is that we've increased our time complexity from linear to polynomial, and we've got O(n) squared. It's quadratic complexity. And we know from the previous theory that this is really beginning to become a poor algorithm. We may not notice it if we've only got a small number of alien ships and a small number of missiles, but as this game scales up, then we start to realise that we're getting some performance issues and we're going to drop our frames per second. So we start to ask ourselves, is there a better way? Can we somehow reduce the time complexity from polynomial back down to linear? Well, as it happens, there is indeed a better way of approaching the problem. Now, it's beyond the specification for OCR, but it's a good indication of how programmers consider the time complexity of their algorithms and the impact that it has on performance, and it's never more noticeable than it would be in games development. And so the idea of spatial partitioning is that we somehow divide the screen into quarters, because we know that the objects that are in the top left-hand quadrant are the only ones that can really collide with each other. And similarly, objects in the other quadrants are the only ones that can collide with each other. And therefore, we're going to significantly reduce the number of objects that we need to check against each other, and we'll reduce the time complexity involved by doing so. So how this would be done programmatically is that you would have a loop that goes through all the alien ships and decides which quadrant they're in, and it adds them to a list for that quadrant. It'll do the same thing for the missiles, and it'll add all the missiles into the quadrant that they belong to, and what you end up with is 4 lists, and you only need to check the objects in each list against the objects in that list. For objects that span more than one quadrant, you simply add them to both lists. It's not a big deal. Now, it won't have escaped your attention that actually when we do this, although we've created 4 separate lists, there is in fact still a problem because we're checking multiple objects against each other, and this could very quickly scale up to becoming a problem again. So what the algorithm actually does is further divide the quadrants into smaller quadrants, if necessary, if the number of objects within a quadrant becomes too large. Now, this algorithm, called spatial partitioning with quad trees, is extremely efficient, and you could have thousands and thousands of objects on the screen all moving simultaneously, and the collision detection algorithm would still be extremely efficient. And if you compare that to the algorithm that we were using before of checking every object against every other object, you'd see that the quad tree approach is remarkably efficient, and you could have thousands and thousands of objects on the screen all moving at the same time, and you'd be able to detect a collision between those objects, and the speed at which the computer can do that is very quick compared to even a smaller number of objects with the nested loop approach. So the illustration here is the quad tree algorithm in practice, and you'll notice that the number of squares we've created here is significantly more than in the previous illustration. But look at the little circles and how many of them actually need to be checked against each other in terms of determining whether they've actually collided or not. And it's quite obvious from this illustration how efficient that algorithm would be. Now, we've made a number of assumptions in our example here. We've used bounding box collision detection, and that's just one way of determining whether 2 objects have actually collided with each other, by drawing an imaginary box using their coordinates and height and width to determine whether they actually intersect or not. So in games development, there are a number of algorithms that we could use for our collision detection, but this is just one example of Big O notation in practice.